Welcome to Lecture 3 of the 11th week of this course. Our topic of discussion for this lecture is one interesting theorem that shows up on page 236 of your textbook. This is the so-called intermediate derivative theorem. Your book calls it the intermediate value theorem for derivatives, which is a mouthful, and in other textbooks, this is sometimes called Darboux theorem after the person who first published the proof of it. So, what is the point of this theorem? Based on what we saw last week, we understood that whether a function is differentiable at a given point is largely independent of whether the function is differentiable at other points. We saw examples where the function is differentiable at all points except one. The one example that this statement should recall for you is the step function. It turns out that there are also functions which are differentiable at a single point but nowhere else. We gave an example of one such function on slide 14.1 of last week. That's in lecture 2 last week. And we saw how even when a function is differentiable everywhere, the derivative function need not be continuous. The prototypical example for this is the function x squared times sine of 1 over x, discussed in lecture 1 of last week. So an academic question is, what sorts of functions can come up as the derivative of a differentiable function? Is it the case that any function can be a derivative? We know that there are functions that are not continuous that still comes up as a derivative. How bad can the derivative be? This is the question that is partially answered by the intermediate derivative theorem. It states that even though the derivative of a function need not be a continuous function, the derivative still must satisfy the intermediate value property. Recall that the intermediate value theorem says that continuous functions have the intermediate value property. But we discussed a couple weeks ago how there are functions that are not continuous but still have the intermediate value property. So the intermediate derivative theorem says that derivatives can fall into this class of functions. A consequence of this is that jump discontinuities are not allowed for derivatives. And this gives another way to check the differentiability of functions, though in this case, you can generally decide using the definition too. Alright, let's get started. The heavy lifting behind the intermediate derivative theorem is this hills and valleys lemma. This lemma is a bit like the opposite of the Fermat's theorem, and the assumptions are very similar. It assumes that f is a continuous function on some open interval ab, and inside this we have 2 points c and d with c less than d, where the function f is differentiable. The reason that we have this larger interval ab is again simply because we have not talked about what it means for a function to be differentiable at the endpoint of a closed interval. So we will just avoid this complication by making the function defined on a slightly larger open interval. The key action will all happen between c and d. So morally speaking, think that we have a function that is continuous between c and d and differentiable precisely at those two endpoints. And here's the key part. There are two different versions of this lemma. First, if we know that the derivative is negative at c and positive at d, then we can conclude that f has a minimum strictly between c and d. Second, if we know the derivative is positive at c and negative at d, then we can conclude that f has a maximum strictly between c and d. At this point, you may feel a bit confused about the significance of this conclusion. After all, since f is a continuous function, doesn't the extremal value theorem already guarantee the existence of the extremal points? The key here is the same as real estate. Location, location, location. Notice that we didn't assume anything about the values of the function at the points c and d. The extremal value theorem tells us that f attains an extremal value somewhere on the closed interval CD. In particular, it is possible that the minimum or maximum are attained at the endpoints C or D. For example, if f were a strictly increasing function, then the minimum will be attained at C and the maximum at D. The hills and valleys lemma guarantee that the minimum or maximum, depending on which case, is attained away from the endpoints. The important bit about the conclusion is where the minimum or maximum is located, not that they exist. Let's start by giving some preliminary parts of the proof. As I already alluded to in the previous slide, since we assume the function f is continuous on the entire interval AB, it is also continuous on the closed interval CD. And so by the extremal value theorem, it has a maximum and a minimum somewhere within the closed interval. Our job is to argue that the minimum or the maximum, depending on which of the two cases you are proving, is not at C or D. The basic proof idea can be captured in this picture. Here, a function is plotted between C and D, looking at the two endpoints. We see that this is a case where f prime of C has positive value, so the function has positive instantaneous slope there. And where f prime of D is negative, so the function has negative instantaneous slope there. The idea of the hills and valleys lemma is that you can think of the continuous function f as the height of a road containing C to D. If you leave C by climbing up a hill and you arrive at D by coming down a hill, then somewhere in between you must reach the highest hilltop of your journey. And if you leave C by descending into a valley and arrive at D by climbing out of a valley, then somewhere in between you must reach the deepest gorge along your path. So, how do we make this work using math? We will prove the second case of the lemma now, where we assume f prime is positive at C and negative at D, and show that f has a maximum in between. The valley case, the first case, is proved similarly, and so I omit it in the video. Just to recall, based on extremal value theorem, we already know that a function f attains a maximum somewhere on the closed interval CD. So the job for us is to prove that the maximum value cannot be attained at C or at D. This will force the maximum to happen strictly in between. The easiest way to approach this is via the epsilon delta definition of derivative. Since we already know by the hypothesis of the lemma that f is differentiable at the point C, so for any epsilon we pick, including epsilon set to equal to 1/2 the value of f prime C, which is positive, including this epsilon, we know there must exist some positive delta such that if x minus c is between 0 and delta, we have the inequality that compares the function f with its linear approximation. Now, look at the portion that is within the interval CD. Since C is the lower endpoint, we care about x that is just above C, where x minus c is positive. Unwrapping the absolute value sign, this means that the difference between the function f and its linear approximation is between minus epsilon times x minus c and positive epsilon times x minus c. Now, look at the first of the two inequalities. We can move the linear function to the left. This gives f of c plus f prime of c minus epsilon times x minus c. Here we have made common factor to simplify. You may wish to pause the video briefly to verify this step. Since we chose epsilon to be 1/2 f prime c, the difference between f prime c and epsilon is positive 1/2 times f prime c, which is positive. So, we can conclude that if x is between c and c plus delta, the value of f of x is strictly larger than f of c. This means f of c cannot be the maximum since we have found some values x between c and d, which is an even larger f value. Now let us look at what happens at the point D. The argument is similar, but since the argument may be a bit confusing, I will go through it again in detail. We will still want to prove the function does not have a maximum at D. By assumption, f prime D exists and is negative, so we will choose epsilon to be minus 1/2 times f prime of D, which is a positive value. Differentiability at D, which we assume is part of the hypothesis, means that there exists a positive delta such that if the absolute value of x minus d is between 0 and delta, we know the function is well approximated by the linear approximation for those x values. Since we are interested in proving that d is not the maximum, we need to try to find some x inside the interval that reaches a larger f value. Since d is the upper end of the interval CD, we are interested in x that is just below D. We unwrap the absolute value inequality and use that. Since x is less than D, the absolute value of x minus D is exactly the same as the value of D minus x. And we find that the difference between the function and its linear approximation is between plus and minus epsilon times D minus x. Again, we focus on the first inequality of the two. And we move the linear approximation to the left-hand side. This simplifies to, after some factoring, f of d minus the sum f prime d plus epsilon times d minus x is less than f of x. In this second factor, notice that f prime d plus epsilon is equal to 1/2 f prime of d from how we chose our epsilon to start with. And since f prime d is negative, this sum is negative. The factor d minus x, however, is positive since x is less than d. So we have f of d minus something negative is less than f of x. Or that whenever x is between d minus delta and d, we find f of x is greater than f of d. And since we found x less than d that has value greater than f of d, this means f cannot have a maximum at d. Just to summarize, the two epsilon delta arguments given just now are to express the fact that if the function f is differentiable at a point c with positive derivative, then at nearby point x that is greater than c, f must increase to get to x. Similarly, if a function is differentiable at a point d with negative derivative, then at a nearby point x that is less than d, f must decrease from x to get to d. Both statements are intuitively obvious. What we provided here are the precise justifications using our definition of what it means for a function to be differentiable. Okay, the Hilton Valley lemma is the main technical aspect of the intermediate derivative theorem. Now we're ready to state and prove the latter. Suppose f is defined on some open interval and differentiable at every point in its domain. Let c less than d be both points in the domain, and gamma a number between f prime of c and f prime of d. Then there exists some z between c and d such that f prime of z is equal to gamma. A perhaps easier way to remember this statement is that if the function f is differentiable, its derivative f prime has the intermediate value property. If you don't remember intermediate value property, this was presented in lecture 3 of week 9, slide 11. It says that if f prime reaches a value at c and a different value at d, then between c and d, f prime must reach every value between f prime c and f prime d. Notice that the derivatives need not be continuous, as we explained in the first lecture last week. So the fact that the intermediate derivative theorem holds need to depend on something else about the derivatives. Okay, let's get started with the proof. First, let's get rid of the easy cases. If gamma is equal to f prime c, then we're allowed to say that c is in the closed interval CD, and so choosing c itself shows the theorem is true. Similarly, if gamma is equal to f prime d, then we can just choose d. So we only need to worry about what happens if gamma is strictly between f prime c and f prime d. What we will do in this case is to reduce to something to which we can use the Hills and Valleys lemma. The Hills and Valleys lemma required the function to have derivatives with opposite signs at the points c and d. This is not satisfied by our function, so we need to transform it. We will look at the function g of x equals to f of x minus gamma times x. Since gamma times x is a linear function, it is differentiable. And so g is also differentiable since f is assumed to be differentiable. We remind ourselves that this also says that g is continuous. The reason we chose this function g is that gamma is strictly between f prime c and f prime d. Since g prime c is f prime c minus gamma and g prime d is f prime d minus gamma, this means that exactly one of g prime c and g prime d is positive and the other one is negative. So this function g now satisfies the assumption of the Hills and Valleys lemma. Depending on which of g prime c or g prime d is positive, we can find either an interior maximum or an interior minimum z. Regardless of whether z attains a maximum or a minimum, we can use Fermat's theorem at z to conclude that g prime z is 0. Now, g prime z is f prime z minus gamma, so this will tell us that f prime z is equal to gamma. So this proof has a lot of similarities to the proofs of the mean value theorems. In fact, this illustrates a general principle. If you want to prove that a function f has a derivative gamma on a certain domain entirely from scratch, the best way is to take the difference of the function f and the linear function with the slope gamma, and hope you can find a maximum or a minimum of this resulting function. Let us consider the following example. We discussed in last week's lecture that this function given by x squared times sine of 1 over x is differentiable at every point on the real line, but the derivative is discontinuous at 0. If we evaluate the derivative, we find that f prime x is equal to this expression. Here, we used the product rule, the chain rule, and the calculus fact that the derivative of sine is cosine. Again, remember that f prime is discontinuous at 0. Notice that when c and d are two numbers with the same sign, then f prime is continuous on the closed interval CD. And so, the intermediate value theorem for continuous function guarantees that the intermediate value property holds for f prime on the interval CD. But what if c is negative and d is positive? By the intermediate derivative theorem, we know that intermediate value property still holds. To understand a bit what is happening here, it helps to visualize what the function f prime looks like. This graph is the plot of the function f prime. As you can see, as we approach 0, the function rapidly oscillates. It is because of this oscillation that we can guarantee the intermediate value property holds, even for an interval that contains the discontinuity at 0. Exactly how this works you have already seen on your problem set for week 9, when you verify that the rapidly oscillating function sine of 1 over x has the intermediate value property across the discontinuity at 0. So I will not spend effort showing you the details. Okay, that's all for this lecture. See you next time.